In this video, we will look in depth into the divergence. So far, you know how to calculate the divergence, and you know what it does, right? So you start with a vector field. Let's call it capital F. And remember, this is a field, meaning that it's not simply a vector, but it's a function of position. It's a vector that depends on position, a vector field. And when we apply divergence, we get a scalar field, which let's call phi of r. And you know how to calculate this scalar field, so phi is the divergence of f, which is equal to the nabla operator vector dot product with f, which is equal to the partial of the x component of f with respect to x, plus the partial of the y component of f with respect to y, plus the partial of the z component of f with respect to z. So that's the calculation, and fine, you know how to do it, we did an example, but what is the divergence really doing? So given a vector field f, if I plot a vector field f, how will the scalar field divergence of f look like? And this is the interpretation of the divergence. So I already gave you a link to a YouTube video that does a beautiful interpretation of this, but to summarize very quickly, if the vector field f, which is represented by these red arrows, seems to be flowing into a given point, so now you can imagine vector f as being a fluid flow, so the flow of water. So if water seems to be accumulating at some point or disappearing at this point, then this is associated with a negative divergence, okay? And this is often called a sink. Now, if the fluid flow f or any other vector field f seems to be emanating from a point, so appearing from nothingness, yeah, then this is associated with a point in which the divergence of the vector field f is positive, and this is usually referred to as a source. And finally, if there doesn't seem to be any appearance or disappearance of the fluid, so the same fluid is coming in to a point than is coming out, then you say that the divergence is 0, okay? So the divergence at that point is 0. These are the most obvious clear-cut cases, but it can be a little bit more subtle. For example, if the fluid coming in has a higher velocity or a higher flow than the fluid coming out, then this also suggests that there is fluid disappearing continuously, right? Because if the fluid coming in is more than the fluid coming out, there must be some disappearance of fluid. So therefore, this situation is also associated with a negative divergence at each of these points. Here, at every point, you would have a negative divergence because the vector field is decreasing in magnitude. And conversely here, if the vector field is increasing in magnitude, so this suggests that at every point fluid is being created and it's joining with the flow, right? So the further right you go, the more fluid there is, so the bigger the vector f, and therefore this is associated with a region of positive divergence, okay? If you have trouble understanding these two cases, let me give you a small spoiler of later we will actually talk about how is the divergence defined mathematically. So how do we define the divergence such that we can calculate it using this equation? Okay, so we'll talk about the mathematical definition. And in the mathematical definition, as you will see, the mathematical definition is nothing more and nothing less than the flux integral, but instead of considering a closed surface, a finite closed surface, we are considering an infinitesimally small closed surface, okay? So in other words, you can imagine a differential of volume. So this is a tiny, tiny, tiny volume in the limit where it goes to 0, around a point. And then you create this surface around this infinitesimally small volume. And this is a closed surface, okay? You can imagine a sphere, although the shape wouldn't matter. The result is the same if the surface is small enough. So you imagine this closed tiny sphere and you calculate the flux of the field flowing out of the sphere. which means that if the flux is positive, meaning that the vector field going out is bigger than the vector field coming in, then the net flux is positive, and therefore the divergence at this point is positive. While if the net flux coming out of the volume is negative, this means that there is more field coming into the volume than there is coming out, and therefore the divergence is negative. So using this trick of imagining the flow, comparing the flow in with the flow out, you can understand if the divergence is going to be positive or negative. And remember, the divergence is a scalar field, meaning that you can calculate the divergence at every single point in space. So at each point, you can imagine this tiny volume surrounding the point, and you think about the flux of the field outside of this volume. Yeah. So let's see some actual figures showing examples of the divergence. So here I'm starting with my starting point F, and I'm plotting it here. So this is a vector field. This is the input. Okay. So if you plot this equation, and this is a vector field because you have x hat and y hat, which means that at every point in space you can find the value of x and y. So x and y has a certain value. So at each point you can substitute x and y into the coordinates, and the result is a vector, something times x hat plus something times y hat, which means that at every point in space associated with an x and y, you get a vector, which is this tiny blue arrow here. Yeah. So at each point in space you have a vector, which is represented by this equation, and this equation looks like this. So as you can see, there seems to be a source here in the center, right? Because there seems to be fluid flow coming out of this point. So there seems to be generation of something at this point. Yeah. And indeed, if you calculate the divergence of F, which is really easy to calculate, you can do the calculation yourself, you know how to do it, we get this equation. And if we now plot this equation, and now notice that this doesn't have any x hat or y hat because this is a scalar field. Now this is a scalar field that depends on position. So what we can do is we can use x and y in the x and y axis, and then plot the color associated with the value of this scalar field, which is the divergence of F. And indeed we see that near the center we are getting high values of the divergence, positive values, meaning that there is a source in the center. Okay, but notice that at every single point in space we can calculate the divergence, and it's given by some value. Okay, so this is one example of the divergence. Let's look at another more complicated example. So this is the equation of my input vector field, which I am plotting here. And notice that this is kind of showing like there is a source here, and then the fluid is doing like this, but there is a sink here, right? Fluid is disappearing in this region. So indeed, if you calculate the divergence of the vector field F, I encourage you, you can try this out. You get this scalar field. Of course, it's much more horrible to write down, but I can plot it in Mathematica. And when you plot it, indeed you get that the divergence is positive around the source, and the divergence is negative around the sink. Okay? So I hope that clarifies the intuitive description of the divergence. Thank you very much for watching, and see you in the next video.